So another differentiating factor in instruction set architecture design is the register model. This is what the registers look like and how they're structured. So most machines are using an orthogonal register file, which is all the registers are general purpose. They have sort of naming conventions that says this register is the stack pointer and that register is something else, but basically they're all accessed the same way. x86 is a little bit unusual here because it started with every register having a special purpose, right? They A, B, C, and D registers, AX, BX, CX, DX, and then SI, DI, BP, and SP. Every register had a special purpose: accumulation, base for addressing, a counter for loops and shifts, and then a data register for multiplication and division, and then a source for string instructions that had special string instructions. It was kind of weird. A destination for string instructions, a base pointer for stack frame references, and then the stack pointer itself. It also had these segment registers, which we'll talk about later. But in x86-64, the modern version of this, these registers are named conventions from general purpose registers. And so they've moved to general purpose registers, but you can still access CX if you need to. And this is important for reverse compatibility that we'll talk about later on. The program counter, how do you deal with the program counter? This is another decision you have to make in an assembly language design. Usually the program counter is only accessible indirectly through branches and jumps, right? You can't go and change the program counter, but ARM implements it as a general purpose register. And we'll talk about why that might be in a little bit. You can think about why that would be a good thing or a bad thing to do. What about the return address? This is usually in the register file, but also it's fixed as a specific register so that it can be hard-coded into, a jump to subroutine or a return from subroutine. Sometimes these things are hard-coded, sometimes they're not. Sometimes they're conventions, and sometimes they're built in. The other kind of pointers that you'll see sometimes are the stack pointer and the frame pointer. This is important for subroutine calls. Usually they're set by convention, but in practice, because everybody's using the same address for the stack pointer, it becomes fixed. And so, although you shouldn't be implementing this in hardware, the stack pointer is always the same register, right? Then you have things like global pointers, where you can put data that is accessible to everyone. You have thread pointers, where you can put data that is only accessible to the thread you're looking for. And then some instruction set architectures implement a zero register, whose only job is to store the value of 0. This is really, really useful if you're going to do comparisons against 0, which is often what happens, right? You set a number, and then you count down to 0, and you check against 0. Having a fixed value of 0 is really important. It's also useful if you want to generate a result, but you don't want to put it anywhere, right? If you want to generate a result by comparing two numbers, but you don't really care about the result, you just care about the comparison, then you can send the result into the 0 register, and the machine doesn't store it because it's just a fixed bank of zeros. And so it's sort of a dumping ground for results that you don't want, which is interesting as well. I said, are we going to put the program counter? Are we going to make that a general purpose register, or are we going to make that a special register? And this is a really interesting consideration to think about a little bit. Branch, jump, call, and return can be implemented directly by the ALU if you put the program counter as a regular register file register, right? If it's accessible to the programmer, if it's in the register file like everything else, you get all these benefits. You can just use the ALU to update it instead of having to have a separate ALU just to increment the program counter. For example, right? Add 8 to the program counter and you get a relative jump, which is just done with the ALU. Now, should you do that? Probably not. Maybe that's really risky, but it can be done. And if you protect code using compilers and assemblers, you're probably okay. The other thing it does is it allows conditional branches and function tables to be implemented with these addressing modes that are available in ARM, right? ARM does this. ARM puts the program counter as a regular register in the instruction register, as in the register file. And so you can use offsets and indexing and branch and base plus offset addressing to calculate the address of an offset in a table, or the address of a subroutine, or anything like that. Lots of really interesting and complicated addressing modes that you can play with the program counter, just like you can do with any other register, and that gives some very powerful kind of interactions to decide where in your memory space to jump to execute the next instruction. But again, it can mess things up if you're not careful. And then the third reason to put the program counter in the register file is that it makes some pipeline optimizations. Because if the program counter is in that same phase, if you're trucking through the pipeline, you're in the execute phase, the program counter is right there. You don't have to worry about like PC plus 4, PC plus 8, you're right there. On the other hand, the program counter value from when you actually fetch the instruction might be different than the one you're looking at now. If you don't put the program counter in the register file, you have to carry it along from pipeline register to pipeline register so that you know what the program counter is if you want to change it, right? These are all just considerations. It can be much more complicated to pipeline with a program counter as part of the register file, but it can also have some advantages. The real problem is that it makes debugging incredibly problematic because you don't know if you're looking at the program counter now or the program counter back then. You don't know if some user code has changed the program counter on you. If you find yourself jumping to a different location than you think you're jumping, it can be very hard to track that down. So most assembly languages today do not implement the program counter as part of the register file. And in fact, ARMv8, I believe they're actually in the process, or maybe have already done so, of removing the program counter as a general purpose register. So it's a really interesting conversation is, do you put the program counter as a general register or do you make it separate? There are other registers that you can use sometimes in a pipeline, in a data path, not just the registers that are accessible to the programmer, but also status registers and control registers and registers that allow you to sort of make decisions about the hardware. The most common one of these is the idea of flags. This is where you have a register that sort of keeps access to metadata about the result from the ALU. If you subtract two numbers and the result is 0, that might be useful in a subsequent instruction. And so you set a flag, you say that the result was 0, and then you can look at that later and say, if that result was 0, then I can take that branch. Different instruction set architectures treat this idea in different ways, right? In many modern instruction sets, we actually don't store the flags, or if we do, we don't actually make them user accessible. We'll talk about that when we talk about the different ways of doing branching. But if you are going to store the flags, there's a couple of different choices, right? Does every ALU operation set the flags, or do you give control over that? ARM gives control over that. You can add two numbers together, or you can add two numbers together and set the flags. That way you can make sure that you know which instruction set those flags so you can make a branch decision afterwards. This is really powerful, and it's really hard to debug, because if you're not quite sure which instruction set those flags, then strange things can happen, right? These hidden states, these hidden variables, can make pipelining very tricky because you have to carry those variables along with you. You don't know necessarily which stage of the pipeline has the flags that are correct for this instruction. It can be very complicated. And so a lot of languages today are actually making these comparisons explicit. Instead of using condition codes to store metadata about a previous comparison, if you're doing a branch, you do the comparison in that branch instruction. And so the next video, we'll talk about the different branching mechanisms in various instruction set architectures.